Bernoulli's equation. Consider a fluid moving through a horizontal pipe that changes diameter. We will say that the fluid here flows with a velocity v2 for reasons that will become clear later. The fluid here is at a pressure of p2. We have learned from the equation of continuity that when the fluid flows into this region of the pipe with a smaller cross-sectional area, its speed of flow increases so that the mass flow rate within the pipe remains constant. We can also observe that the pressure of the fluid, P1, in the smaller diameter section of the pipe is less than the pressure of the fluid in the larger diameter section. We have also learned about how pressure changes with depth in a static fluid. An observation that follows from this is that if a fluid moves from a lower elevation to a higher elevation, the pressure at the lower elevation is greater than the pressure at the higher elevation. For a flowing ideal fluid, Bernoulli's equation tells us how the pressure and speed of the fluid change with elevation. We will derive Bernoulli's equation using the work-energy theorem. Remember that the work-energy theorem says that the net work done on an object by non-conservative forces equals the change in the total mechanical energy of the object. Pressure within a fluid is caused by collisional forces between particles, and these forces are non-conservative. That means when a fluid is accelerated due to a change in pressure, work is being done by non-conservative forces, and the total mechanical energy is changing. For our fluid moving through this pipe, we will say that the mass of this lower fluid element is the same as the mass of this higher fluid element. The pressure, speed, and elevation of the fluid element at the lower point, however, have different values than they do at the higher point. The total mechanical energy on our fluid element at any time in this case is the sum of the translational kinetic energy and the gravitational potential energy. When work by external non-conservative forces is done on the fluid element, the total mechanical energy changes. The net work done by the non-conservative forces is equal to this change in total mechanical energy. Substituting in for the kinetic and potential energies, we find a relation involving the total mechanical energies in the two regions of the pipe. If we consider the fluid element at a point between the two elevations, we can look at how we get the net work by non-conservative forces. On the top surface of this fluid element, the pressure from the fluid above is given by P. The force from this pressure is F equals P times A, the surface area of the fluid element. On the bottom surface of the fluid element, the pressure is greater and has a value of P plus delta P, where delta P is the difference in the pressure between the bottom and top surfaces of the fluid element. The force from this pressure on the bottom surface of the element is F plus delta F, and equals P plus delta P times A. The difference in these forces is delta F, and is equal to the net force pushing the fluid element up the pipe. Remember that linear work is equal to the magnitude of the force over the distance the work was done. So as this middle fluid element moves through this distance S, this gives us the work done. The surface area A times the distance S is also the volume of the fluid element, so the work is V times delta P. Delta P is P2 minus P1, so that gives us this for our expression for work done by non-conservative forces. Plugging this expression for work done by non-conservative forces into our work-energy theorem gives us this expression. If we divide this expression by the volume V, we can eliminate this term and substitute the density rho in for the mass over volume terms. When we do this and rearrange terms, we get the expression that we call Bernoulli's equation. Bernoulli's equation gives us the relation between the pressure P, the fluid speed V, and the elevation y at any 2 points in the steady flow of a non-viscous, incompressible fluid. Since this equation holds true between any 2 points in the fluid, we can say that this term from either side of the equation remains constant throughout the fluid flow.